So lecture 19, rearrangements. So where did we leave off? Last time, we saw that infinite, I love how, who was it? Maybe Joe. Somebody said infinite summation is not commutative. Right? And we saw examples of why that's the case. So then the question is, well, what does happen to infinite summation? We saw last time we proved two theorems. Which two theorems did we prove? First of all, if a series converges, then the terms go to zero. We proved that last time or the time before? What did we do last time? No. The alternating was the second one. Absolute. Thank you. Absolute convergence implies convergence. Okay. So if this sum converges, which people write is less than finite because the only thing it could diverge to is infinity because it's all, it's an increasing sequence. So it's either bounded, in which case it's convergence, or it's unbounded, in which case it diverges to infinity. It's monotonic, right? The terms are non-zero. So if this series converges, absolutely, then the original series converges. Okay. And then we did the alternating, not alternative, alternating series test, which is if you have a sequence AJ going down to zero, it has to be antitone and have limit zero, then the alternating series converges. Not necessarily absolutely. Okay. So this is one of those rare, so this is the main question. So here's the problem. This is one of those rare moments in mathematics or life where we're going to get a complete, clear, and beautiful answer to the question of when is infinite summation commutative. So I have two theorems for you today. Theorem one, if a series an, well, summation an, you know what I mean, is absolutely convergent, then infinite summation is commutative. Infinite summation is commutative. And we'll make this precise in a minute. Basically, sum the terms any order you like, and you're going to get the same answer. Theorem two, if not, if a series converges but is not absolutely convergent, then infinite summation is not only not commutative, it's as non-commutative as possible. Okay, this theorem has a fancy name. This is often called the Riemann Rearrangement Theorem. Riemann Rearrangement Theorem. And what it says is you pick a target number L for any target. Target meaning that's what I want the limit to be. Target L in minus infinity to infinity, including minus infinity or infinity. There exists a rearrangement. Just swap the order in which you sum the terms. That sums to L. If you have a sequence that's only conditionally convergent, it's not absolutely convergent, but it is convergent. It has to be convergent, or else you don't know if you don't have anywhere to start. Thank you.
Sequence converges. How can you get infinity?
If the sequence itself converges, but not the absolute value, then you can change the order of which term goes where, so that your sum goes off to infinity. In the order that it arrived to you, yes. But not in the original order. but not in some other order, some shuffling. Okay, so let's understand these two theorems. That's our goal. So first of all, what do I mean by a rearrangement? Okay, so let's talk about rearrangements. This is a very simple concept. By a rearrangement, so definition, a rearrangement, well, what do I want a rearrangement to be? I want to sum A, but not of n. I don't want to sum it in the order that they arrived, but I want to sum it in some other order. Well, out to infinity, but in some other order. So let's call this sigma of A. But sigma is not a subsequence. I don't want to skip some values and keep them in the same order that they were. I want to completely change what order. So it's like almost the opposite of a subsequence. It's not going to be monotonic. All it's going to do is make sure that it hits every value at least once and no more than once. Okay, so a rearrangement sigma is a function from the natural numbers that shuffles the natural numbers. That shuffles n. Okay, so it has to have two properties. It hits every number. It doesn't miss anything. I don't just shuffle everybody, but I forgot to tell you where one goes. It hits every number and never repeats a number. Never repeats a number. Okay, these two concepts make up a rearrangement. They have technical terms. Sean?
Is this like a bijection?
That's exactly what a bijection. Yeah. So another way, what we call a subsequence is usually just called a strictly monotonic sequence. What we call a rearrangement is simply called a bijection. So rearrangement is the same thing as what people call a bijection. And let's unpack these two things. So hits every number has a fancy name. Surjection. This is a surjection. Surjection. And never repeats a number. Injection. Good. So let's make these precise. So definition. A function f from x to y, just completely abstractly. You have some function from something to something else. Is surjective if what? I want to know that I surject onto something.
Like lowercase y, capital Y.
Yep. And let's be type theorists. Yes.
There exists an lowercase x and capital X such that f of lowercase x equals 1.
Beautiful. Okay. So x is some abstract set. Y is some abstract set. No matter what point you choose here, little y, there's always some x in x so that f maps x to y. So everybody here gets landed on. That's what surjection means. We hit every number. We don't miss any number in the range. Okay, that's surjection. Let's talk about injection. Definition, again, completely abstractly, a function from some space to another is injective if what? Here's my x, here's my y, here's a bunch of points, here's a bunch of points. John.
All x, x1, x2. If f of x1 is equal to x2, then x1 is equal to.
Beautiful. Perfect statement. Okay, if I have 2 points, x1 and x2, and f takes them to the same value, f of x1 and f of x2, if they happen to clash, well, the only way that can happen is if you started with the same point. Of course, if you start with x1 equal to x2, you take them somewhere and they're going to land on the same value. That's the only way that can happen. Okay, that's injection. You never repeat a number. If you both hit every number and never repeat a number, then all you're doing is reshuffling the elements of x and y. Okay, that's called a bijection. Mathematically, something that's injective and surjective is bijective in both directions. And we'll call that a rearrangement. Okay, So now let's give a formal statement of theorem 1. So let's do a formal statement of theorem 1. Again, it says if a series converges absolutely, then infinite summation is commutative. Doesn't matter in what order you do things. So let's say it like this. Assume, okay, we're given the objects. The object, I guess, is a sequence A in the naturals. We have assumptions. What was this called? Abs conv. So let's call this HA. Abs series conv. Anybody remember? Abs series conv A. In other words, the summation AN converges. And our goal is to show that there exists an L, a value L, so that the original series goes to L, series lim AL, and for any sigma that's a rearrangement, the series A composed with sigma. A composed with sigma is just reorder the terms of A. Also has a limit, and that limit is the same value L. No matter how you reorder this, we're going to get the same limit. Okay? Why is this going to be true? How could this possibly be the case? Tough.
So I think somewhere we're gonna have to use the fact that this series itself is all positive, so it's like monotone.
Okay.
And the fact that it converges, it's all going in one direction and it can't go out to infinity. So maybe like you establish some bound and path to get there, and then the limit like will turn to going to 0. So like you just like remove all the other options. It's just something that's left.
Yep, I like it as an intuition. I like it as intuition. How do we, well, a few things we can get started right away. Let's make a little bit of progress on this goal right away. Akil. Exactly. So exactly. So what was that called? Maybe ab series conv of series conv or something? Let's see. Theorems about, oh, I tried to organize the theorems because it was getting, this list of theorems was just getting insane. So I tried to organize them by whether they're about sequences or just general theorems or something temporary that we, just don't need to keep around, or something about series. So this is called converges of absolute series converges. Okay, so conv of, and I tried to change, some of them were capital ofs. I made it all underscore lowercase of underscore just to keep a uniform thing, because I can't keep track of which is which. Of abs series converge. And if I feed into that HA, that will tell us exactly. So this says that the series A converges. Okay. The series A converges. Okay, so if it converges, then it converges to something. The definition of convergence is that there exists an L so that it converges. So let's choose LHL using that. Okay, so what does HL say? L is a real number. HL says yeah, we don't have to go all the way down that far. Just in broad strokes, John? Exactly. Series lim AL, or maybe depending on how, in what order we did this, it might say instead, seq lim, series A, L. Either way, those are, that is what series lim means. So those are the same things definition. Okay. So we have our L. So what's the first thing we want to do? Use L. Use L. Now we have to prove that seq lim A is L and yada yada. Split them. Split ifs. I'm sorry, split ands. These aren't ifs, these are ands. Split ands. And the first goal will be that series lim of A is L. Apply HL. That's exactly what HL says. Okay, so now our goal is to show for all sigma that's a rearrangement, series lim AL. So the next line is intro sigma, and H sigma. H sigma says it's a rearrangement. Okay, so now we know HL, we also know H sigma, which if we unfold the definition of rearrangement says injective sigma and surjective sigma. Okay. We haven't made that much progress because we still have no idea how to prove that the series lim A sigma is L, or equivalently that the sequence lim of series A composed sigma is L. So now let's sketch. Okay, let's go back to sketching. Sketch. The B, yes, please.
I think like if you can show that it has to be less than or equal to L and greater than or equal to L.
If it converges.
Which it has to, right? Because oh, we need to prove that.
We don't know yet that it converges.
No, we have like this here. Oh, this is not theorem about the absolute convergence.
Well, it's sort of begging the question to say, you want to say, well, the absolute, we will know that it converges if its absolute value converges, and the absolute value of the original one converges. So if you reverse the orders, oh wait, that's what we're trying to prove, regardless of whether it was something about positive or not. Okay, so what's the beef? We're trying to show seq lim A sigma L, right? So the idea is, at some point, we need to show something like a sum of A sigma K, as K goes over the range of N, minus L is less than epsilon. Okay, the beef is need to take N large so that we get this inequality. Joe, you got a question? You got an idea? Tell me.
It's gonna be tricky to explain.
Yeah.
I feel, okay, so you know that the sequence, the series absolutely converges.
Yes.
So once you intro the epsilon in this solution, in the goal, right, you can use that epsilon and you get that, okay, the sum of the absolute value of K range N.
I'm going to write what you're saying. The sum of the absolute value of A sigma K? Just the original.
Just regular.
Love it.
In range N is that the distance to L is less than the same epsilon for some N for all. Okay, I have to go back to the statement.
You're on the right track.
We've introed the epsilon from the solution. We're specializing this statement to that epsilon.
Yeah, which statement? HA? HA is the fact that A converges absolutely, or HL, which is that A itself, not with absolute values, converges to L.
I'm not sure exactly what we did, but let's try HL.
Okay, it turns out you need both, so go on. There was no wrong answer to that one. Let's try HL. Okay, so HL, what does HL tell us? Very good. Let's go into what does HL tell us. HL will eventually imply, what's the beef of HL? If we take M large enough, then if we sum AK with K up to M
We can get it arbitrarily close
to L, we can get it arbitrarily close to L. Yes,
the idea I have here. is that,
Yes.
You know, since sigma is a bijection.
yes,
All the values in range M will appear somewhere. We just have to make the notion various.
that's exactly right. So that's problem one. That is exactly what we need to do for problem one. Oh, sorry. That's problem one and problem two, which can come in either order, and I did it in the other order. So let's follow your nose. You're exactly right. The idea is that the image, do you guys know what the image, what I mean by the image? The image of sigma on range N, in other words, take the set, this is the set of all values of sigma of K as K ranges in range N. Okay, so the idea is that this will contain range M. If you have a bijection, then if you go far enough out, you have to contain all the first M numbers. Okay, we have to prove this, but is that the idea that you're going for?
Yeah. Technically, some point Since for every output, there is some input that maps to that output. You can eventually cover all that needed outputs by going far enough.
Exactly. So by the way, you remember when we looked at that matrix, this -1s and then a half and a quarter and so on, and zeros over here? And we summed this way and then that way and then down as opposed to down and then across? Were those rearrangements? Technically, no. Because we would have to sum infinitely far this way before we would even start summing this term. Okay? So they're not really rearrangements. They can approximate rearrangements. You can go really far out this way and then restart over here and go over here and keep going over there and then restart over here. But you have to be, what a rearrangement has to do is because the rearrangement we did there does not satisfy this. So it's not actually a function. I mean, it was just a drawing. We were using our intuition, but it is not an official rearrangement. Daniel.
What was supposedly a rearrangement of what?
This is what we discussed last time. We had this doubly infinite matrix.
Right.
And we summed all the rows and got a value and then summed those values. Or we summed the columns and got values and summed those values. And we got a different answer.
Oh,
And so the question was, is this a rearrangement? And the answer is no. Because you can't say sum infinitely many terms over here, and when you're done, come back and sum these terms. Because you're not done. You're not ever done. It's not going to be surjective. You can go in any order you like, but you have to have an order that eventually hits every number. And that's the point. That's exactly what this says. If you actually have a rearrangement, then eventually, for any value of M, you can go far enough out in N, and the image of sigma on the first N numbers will cover the first M numbers. So however you're reordering things, go ahead and do it, but you can't escape at some point getting the first M numbers. Does that make sense? Sean?
range of M subset, the image and not the like, would you want, like when you have like an M that you take from HL, wouldn't you want like in the original statement for that subset or that image to cover at most everything that's in M, so that way that you can like bound like the first thing by the second thing, or
So that's the question. What's the difference between this and this? So let's say M is really large, so large that you get within epsilon of L. When you sum them in order, the first M. Well, this sum, if n is large enough relative to this m, then this sum will in particular contain the first m values, but it'll also contain a whole bunch of stuff after that at random intervals.
Oh, wait, sorry, yeah, I understand that.
Does that make
Because
sense?
The more values that you add, I was like confusing it because I didn't realize the more values you add, the closer you get to L, and thus you get a better approximation.
Yes. So these, if you sum them in order, will give us a very good approximation to L, arbitrarily close, by taking m large enough. But then you make n even much larger if need be, so that the values that sigma takes along this range in particular include the values that the original 0 through m minus 1 terms took. Does that make sense? Gil? Yes. That's right. The snaking thing is a rearrangement. What we did is not a rearrangement. That's all I wanted to point out. So let me just write that. Note our matrix row versus column summation is not a proper rearrangement, because it doesn't satisfy this condition. Okay, so let's put a pin in this for a second. Let's say we agree that that's true. Seems to be that's what should happen. Then the idea, let's just continue the idea, is that when you sum k from 0 to n of a sigma k, and you subtract off L, you can also subtract off a sum as k goes from 0 to m of a k, and then add back in a sum as k goes from 0 to m of a k. And that thing will be at most this plus this. This part we can make less than epsilon. We can make it less than epsilon over 2 if we like. What are we going to do about this part? Akil. Very good. How? Think about what this says. This, we're summing. Okay, so let me try to draw a picture. It's very hard to draw pictures for this thing. This sum is from 0 up to m, everybody. This is range m. Range m, there's m. Okay? Sigma, I don't know what the hell sigma's doing. Sigma of 1's over here. Sigma 2 is over there. Sigma 3 is over there. Sigma 4 is over there. But n is so large that actually I have to contain all of this stuff and then a bunch of other random stuff. So what can you say? So this is the image of sigma on range n. So what can we say about this difference? We're adding up some terms. I claim that what we can say about it is it's the sum. This is equal to the sum over some set S, k in S, of AK, where S is this stuff, is some finite set. And what can we do with this, the absolute value of this? Yeah, go ahead, John. Triangle inequality. Yes. Beautiful. We can bring the absolute values inside. I agree completely. But now what? Joe?
It's absolutely convergent, so the terms go to 0, and once m gets large enough, we know all those terms we know k is at least greater than m. So we can make that arbitrarily close to 0.
Keep going. Why?
Because since it's absolutely convergent, we know the terms A of n must go to 0.
We need much more than that, but you're so close. The sum over K and S over here is like the tail, but just a finite sum. It's just a finite sum. So what about the fact that the series is absolutely convergent? Have we not used yet? Series converges if and only if it's Cauchy. Ah, and what does Cauchy say?
The terms and fields. Oh.
If you take the entire interval, as long as m is large enough, if you take this entire interval, however far out it goes, so this is at most a sum of k in ICO, the interval from m up to some max, capital M, of absolute value of ak. And that we can make less than epsilon over 2 by Cauchy, by the Cauchy of, absolute value of A. That's the argument. Daniel.
Wait a little more. How is this series?
Yes. So the fact that the series is Cauchy, let's remember what that means. Let me go back to a normal color. Again, the fact that the sum of AKs as k goes from 0 to n minus 1, this sequence is Cauchy. Means for all epsilon, there's an n, yada, yada. If I take the sum up to m minus 1 of absolute value of ak, and I subtract off the sum up to n minus 1 of absolute value of ak, I'll get that to be less than epsilon. So, but what is this? This is the sum of ICO from n to m. It's just an entire interval. Whatever this set is, it's contained in an interval. And Cauchy says we can make that as small as we want by taking things large enough. Okay. So let's unpack all of these things in pieces and then put them together. So far, so good? Everybody with me? We're getting to the real stuff here. So, in fact, yeah.
So you said basically we can go as far as we need to until those terms don't matter. Like,
Until they're bounded by epsilon over 2, yeah.
but one thing like I'm concerned about is the farther you go in this case, though, you keep getting new random terms.
That's right.
So like, how do we like know that you're not adding like?
Because look at what Cauchy says. It says for all epsilon, this is essential. Now you're going to see the power of Cauchy. There exists an n, so that for all n at least n, and for all m at least n, no matter how much farther out you might need to go, you'll still not add up to, this difference will still be less than epsilon. In other words, this sum, no matter how much farther out m needs to be, will still not exceed epsilon over 2. Regardless of how bad this rearrangement throws some of the values, it doesn't matter. That's the amazing thing. Akil.
Capital N, like the maximum image of n minus 1.
Yep. And what are we going to replace that with? The sum, because we're lazy. Yep. Let's be really, really crude about what this possible upper bound could be. Okay. So now let's look at what the first task is. The first task is if we have a series, I want a more flexible version of Cauchy. We have a series that's absolutely convergent, and we're given a positive epsilon. My claim is that there's an n, so that anytime you have a finite subset of the natural numbers, can you guys see this? Should I make it a little bigger? Yeah, a little bigger. How's that? Better? Let me write it as we talk about it. Come on. There we go. Okay. So, theorem. This theorem is called strong Cauchy of abs series conv. Whatever. That's naming things is not my forte. Strong Cauchy of abs series conv. Okay. The theorem says you have a sequence AN and you have an assumption HA abs series conv. You have an epsilon and you have H epsilon, that epsilon is positive. And your goal is to show that there exists an N so that for any S, which is a finite set, thin set of the naturals, so any finite subset of the naturals, if there are no elements in S that are at least capital N, so the fact that for all K in S, K is at least capital N, I guess with an equal sign, doesn't matter, that implies that the sum over K in S of the absolute value of AK is less than epsilon. Okay, so this is a more flexible version of being Cauchy. Being Cauchy says that the entire interval from, as long as you start at least at this capital N, the entire, whatever set you take that doesn't contain any terms from the first N terms, the difference will be at most epsilon. All right, let's make sure we get through all of the natural language stuff, and then we're going to come back and fill in the formal details. Do you believe that this is true? How would you prove this thing? Proof. What's that?
What?
We can't use 0 because the first term of A could be 1. And then we'll never get below epsilon.
Oh,
We have to make sure that we discard the first capital N terms, and then the tail is what it is. Okay? So the proof is, well, how large should we take this capital N?
overall.
You just get it from Cauchy. It's the same N. It is the Cauchy N. Okay? So the proof is choose N Hn using what? I know that the series is convergent. I want to know, I know that the series is absolutely convergent. In particular, that means the series is convergent. In particular, that means the series is Cauchy. So is Cauchy of whatever it's called, seek conv HA. I think that'll do it. So we get an N that has this property. Let me speed this up a little bit. That tells us that now use that N, and then intro S and HS. Intro S and HS give me the finite set and the hypothesis that for all elements in the finite set, they're at least capital N. Then I want to know that this thing, so now this is my goal. The Cauchiness says, let M be the max of the elements in S, max over K as K ranges in S, by which, of course, we're going to change that to the sum. Then the sum over K in ICO, capital N to M of absolute value of AK is less than epsilon. And this is an upper bound for the sum over K in S of absolute value of AK. Okay, so hopefully at least the natural language just makes sense. Brandon.
What's that? Like capital.
Capital M is the largest entry of S.
Okay.
So S is, I'm thinking of S as this red thing, or I guess it's, red is the entire interval and purple is the part that's not in the initial. So I have some set, but it doesn't have any elements that are small. And I want to show that this will be less than epsilon.
The max, or is it like, I mean, if it's the max, then you need to include an M. So you need to be ICC. Like for your sum. As the sum like ICO, it just needs to
1 plus?
Oh, 1 minus.
It wasn't there when you asked the question, but yes, 1 plus, just add 1. Okay, we're gonna need a few theorems for this. The theorems are, here's some new theorems. Mem ICO, when are you in ICO? It's an if and only if. We'll come back to, I'll just click on it for a second. It says that you're in ICO if and only if you're less than or equal to the lower part and strictly less than the upper part. Very simple. You might imagine where we would need that. Sum less than or equal to mem of non-neg says if you're summing a bunch of things, this is so hard to see. Here we are. If f of I is less than the sum over j and s of f of j, if I is contained in s and all the terms are non-negative. Okay, so this is saying you can sum a bunch of things and that'll be an upper bound for an individual term. As long as the individual term is in the set that you're bounding and the set that you're summing and all the function values are non-negative. Sum LE sum. Term LE sum. Do we already have this theorem?
I think terminally sum is just like a weak version, and it's only from like 0 to 10.
Oh.
Yeah, this is very good. This is from 0 to m. So now we don't need term LE sum anymore. We have a better version of it. Another one is sum LE sum of non-neg. This says if you just have the other theorem is a special case of this theorem where I guess S is a singleton. So you don't have to convert back and forth. So if the terms are all non-negative, then when you sum over a subset, the sum can only get larger. All right, so I think you will be able to put those pieces together and solve this. Let's look at the next. Let's look at the next theorem. Here's the rearrangement theorem. Eventually covers of rearrangement. So are we happy to move on from not prove this strong Cauchy of ab series conv right now? Okay. Theorem 2. Theorem 2 is called eventually covers of rearrangement. It basically says exactly what we were just talking about. If sigma is a rearrangement and you give me a number m, then there exists an n so that for all n at least capital N, the first m numbers are inside the image of sigma on the first n numbers, as long as little n is large enough. Okay, so let's write that down. This is called eventually covers of rearrangement. And we're given sigma. We're given h sigma that it is a rearrangement. And we're given a natural number m. And our goal is to show that there exists some n so that as long as you take at least that many elements, the image of sigma on range n will contain range n. This is actually very simple to prove if you think about it for a second. What's the idea? Yes.
Take like max of sigma 1 to n.
That's a good idea. The problem with max of sigma 1 to n is that how do I, like, sigma, again, remember what sigma is doing. Sigma is putting the first number over here. This is 1, and this is 2, and this is 3, and this is 37, and this is 25. So how do I guarantee?
Oh, wait, I wasn't here, but Art just said it was like a bijection.
It's a bijection, exactly. Rearrangement is a bijection. So let's get the inverse map. Exactly right. Exactly right. Let's remember what surjectivity means. So H sigma dot 2 is the surjectivity. And surjectivity means for any element in the target, in the range, there's some value in the preimage. So H sigma 2 says for all, let's call this M, there exists an N such that sigma of N is equal to M. Right? That's what H sigma 2 says. But what is that? Sean?
Like
defines the sequence.
It defines a sequence. For any m that exists in n. That's our fancy choose. That's how you get the inverse. Exactly right. So if we choose, let's call it tau, h tau, using h sigma 2, that gives us a function tau on the naturals. So it takes an m and gives you back the n. And h tau says, for all m, sigma not of n, but of tau of m, gives you back m. Tau is the inverse function. Okay, so now I know 37, well, 37 is over here at 5. So tau of 5 is 37. And what do I want? If I want to go up to m, if these are the numbers I'm hoping to cover, if you want to cover the numbers from 1 to m, Sean,
You just want the
you just want the max. Yeah, exactly. The max over the elements in range m of tau of k, maybe plus 1. And instead of the max, we'll just make it a sum. Okay, that's the n that we want. So if that's our n, then use that n, intro nhn, intro nhn. Okay, now we have to prove that one set is contained inside the other set. Have we talked about how to do that? The definition of one set being contained inside another set is that for all elements of this set, so this is equivalent to, for all k in range m implies k in image sigma of range n. We could change, or we could just directly say intro. So intro k hk. So this hn says that n is at least capital N. hk says that k is in range n, range m. Okay, what does it mean to be in range m? I have to give you a little theorem for that. So we have a definition. Okay, we have definitions: injective, surjective, and rearrangement. And a new definition is non-empty and image. Yeah, I have to add image to this list, and I have to add non-empty to this list because it depends. Wait a second. Non-empty I needed for the last one. What happens in the last one? What happens in the last theorem is that when you intro SHS, S might be the empty set. And if S is the empty set, then this is the wrong thing to take. Because, well, because it's too many elements, yeah. Well, this is 0. I don't know. I broke in my head, I broke it into cases, but I don't think I actually needed to break it into cases. Anyway, so that should be on the previous line. The image we need here. Image I should have highlighted as something else. So what is the image of sigma? So what does it mean to be a member of the image? There are a couple of theorems that are missing. I have to add for you. Oh, I did say mem range, right? Or mem ICO or something. Mem ICO, I think I mentioned. Mem range might be useful. K is in this range if and only if what? It's less than m. Yeah, exactly. And how about mem image? Mem image. So K is in the image of the range n. Exactly. Mem image says, now the new goal, instead of saying I need to show that K is in the image, it'll say there exists some J such that sigma of J there exists some J in range n, so that sigma J is equal to K. Okay, so which value of J should I use? Sean? Tau of K, exactly right. use tau of k. Okay, you guys get the point. I think you can finish this one too. We're running low on time, and I want to make sure I at least hit. I don't want to spend more time on sequences and series. We have to move on to actual functions and do some calculus. But this is important. This is the big boss. So here's the original, the first rearrangement theorem. If you have an absolutely convergent sequence, this is exactly what we were talking about before, a series rather, and sigma is a rearrangement, then there's an L so that A converges to L and any rearrangement converges to L. And now I think you can smell exactly what these things we're supposed to set up. The first says you take M large enough so that you take M, it's right here. You take let's see, it's right here. You take M large enough so that when you add and subtract this, you get a difference, and that difference is something, but S needs to be taken large enough so that by the Cauchy property of the absolute value, you get at most epsilon over 2. Meanwhile, because A itself converges to L, this difference is also at most epsilon over 2. You put those things together and you get the rearrangement. Okay, let's get the last. Will you agree to not go through the details of the proof right now? Maybe we'll have 5 minutes left because I want to get the biggest boss, this conditional convergence theorem, what people call the Riemann Rearrangement Theorem. So this is where non-commutativity, if you're not absolutely convergent, then infinite sums are as non-commutative as possible. So again, I do have to assume that the series converges. If the series is just A of n equals n, then there's no talk of rearranging anything. Daniel.
So, just for clarification, the rearrangement theorem just says if A is absolutely convergent, then something.
Exactly. Then A, the sum converges, and B, sum at any order you like. Okay? This says if it's only conditionally convergent, it is convergent, but not absolutely convergent. Then for any real number L, you give me a real number, I should be able to return to you a rearrangement of those numbers so that the sequence summed in that order converges to L. Amazing. Okay, so let me explain to you the idea of this theorem, and then we certainly won't have time to prove it. In fact, I decided at some point last night I had enough and I didn't finish the proof. So if any of you actually can prove this, I'll give you 10 bonus points if you can prove it formally. I think this is actually pretty hard to prove formally, and you'll see in a second why. Okay, so theorem 2 or theorem 4, whatever, this is level 4. This is the actual Riemann rearrangement theorem, which I call the conditional convergence theorem. Convergence theorem. Okay, so we have a sequence A. It's conditionally convergent. So HA, conditionally convergent means it's the series converges. I guess I call this HA1. Series converges A, and HA2 is it's not true that absolute value series converges A. So these two things I could have made into a definition called conditional convergence. Conditionally converges A. Okay? And then our goal is to show that for any L, there exists a sigma, which is a rearrangement, and the series converges, series lim of A composed with sigma is L. You give me a target. By the way, this is about real values, but you can also, as you'll see in a second from the proof, can go off to infinity or to minus infinity if you so choose. Okay, it's as non-commutative as possible. What's the idea? Any thoughts? You're trying to get to L. So here's your favorite value, L. You have some random series, you know nothing about it, except that it converges, and it doesn't converge absolutely. Sean.
So, like, maybe you would try to get past L and then go down after you get past L, and then like oscillate back and forth so you can kind of get closer and closer.
That's exactly it. Okay, that's the whole idea. The whole idea is two things. The series converges tells us that the terms go to 0, okay? So the terms themselves, the ANs go to 0. So what we're going to do is, the idea is let, I don't know, a pause or something be the sequence if a n, so this maps n to, it's a function that maps n to, if a n is positive, then give me a n, else 0. In other words, just the max of a n is 0. So these are the positive terms. And then a neg will be the negative terms. So this is max of a, I guess, negative a and 0. So if a is negative, so some values of a, here's the original sequence a. The original sequence has some positive values, some negative values. They're not, it's not monotonic. It's, you know nothing about it other than, however, for whatever reason, it converges. Okay? We need to prove two things. Two things. So HA pos is that diverges to infinity, if you remember that, to infinity, A pos, and HA neg diverges to infinity, or the series diverges to infinity, and series diverges to infinity, A neg. Okay, what this says is you sum, I'll call these A plus N. So these are all non-negative. This goes off to infinity, and the sum over the negative terms that I've made positive, those sum to infinity. If not, then what? Notice that the sequence A is just the difference of the positive terms minus the negative terms. So if one of these, let's say this one converges, let's say the negative terms converge, right? I claim both of these things is true. So if at least one of these things is not true, let's say the positive series converges. Well, then either this also converges, in which case their difference also converges, and we have absolute convergence. Sorry, their sum is the absolute value. The point is that the absolute value of A is A plus plus A minus. So if they both converge, then the series would be absolutely convergent. So at least one of them diverges. But if one of them diverges and not the other one, then the sum would be a sum of a convergent and a divergent sequence. So the series itself would also diverge. It would not be a convergent sequence. Should I write all that out, or let me just idea? So the reason both of these are true, the idea is, well, maybe the plus one is there are four cases. There's the plus sign and the minus sign. Okay. There's the plus sign and the minus sign, and there's diverges or converges. Okay. These are the four cases. If the plus sign, sorry? I drew it wrong. I want to say this is for the plus sign. The plus sign diverges. The plus sign converges. The plus sign, the minus sign, Jesus, diverges. The minus sign converges. Okay. If both the plus sign and the minus sign converge, then it's absolutely convergent. So that's wrong. If the plus sign, if you're in one of these corners, the plus sign converges but not the minus sign, then the series itself can't converge. So it's not true that series converges. Same thing here. It's not true that the series converges, because you're adding finitely many negative things and infinitely many, or positive things and infinitely many negative things. And so this is the only thing that can happen. So actually both of these things go off to infinity. And so what that means is, no matter how far out you go, so for all n, let's just work with the plus one, there exists an m after n such that, and for all n and for all value of x, for all x positive, there exists an m after x, so that the sum in ICO n to m of a plus k exceeds x. And then you do exactly what Sean said. Okay, so what you do if you're trying to hit L is, first you give me a bunch of plus values. So give me the plus, give me a plus, give me a plus, give me a plus, give me a plus. The first time I go over L, switch and start giving me minuses. I got a minus here, I got a minus here, I got a minus here. I'm going to do a bunch of minuses, a minus, a minus, a minus. Oops, I crossed L. Now I go back up. Plus, 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 I crossed L again. Minus, minus, I cross L. I can always keep crossing, no matter how far over I am. If I go far enough, no matter how far over I am, if I go far enough, I'll be able to find a bit that gets me that much further down or up. And the individual terms, since every time you cross, you switch what you're doing, the individual terms go to 0. So this process is, if it overshoots L, keeps overshooting L by something that's going to 0. So it gets closer and closer to L. Formalize that. Write out exactly what it means for that sigma. Whew. Okay, so we're going to leave that be. But let's, at least in the last 10 minutes, I'll show you what the proofs are of the other 3. Does that make sense? Any questions? Have we understood this mathematically? The most important thing, I do want you to understand this proof. Okay, obviously I haven't given you a formal, I mean, I've given you the proof that's in every textbook. I looked, I was curious how they did this in the library. It's not in the library. At least I didn't see it. I don't know, I did a quick search. I didn't see this Riemann rearrangement theorem, that you'll get any limit you want by rearranging the terms if it's not absolutely convergent. Okay. Let's go back over any questions on the conditional convergence theorem. So we've now hit the big 4 theorems: the conditional convergence theorem, what people call the Riemann rearrangement theorem, that you can get to any value you want if you're not absolutely convergent but convergent. The what I call the rearrangement theorem is the absolute convergence theorem, which is this main theorem. Yeah, if you're absolutely convergent, then go ahead and reorder any way you like. And the other 2 most important theorems is that absolute convergence implies convergence and the alternating series test. For me, those are the big 4 things. If you know those 4 things, you know something about series. The contrapositive is, if I haven't taught you those 4 things, then I haven't given you a proper course in real analysis. There are lots of other things about series that we should know that we won't have time for. But as long as I hit those big 4, I'm satisfied. All right, let's get to the proofs. So let's go in reverse order, I think. Let's go in the same order as there. So let's go back to theorem. Where's our stronger Cauchy? I think that's the first thing. Okay, strong Cauchy. So here we are. Let's just jump straight to here. So this is level 1. Go away. Okay, strong Cauchy. I'll just grab my solution and show you what it is line by line. It's not so short because there's a lot to do. But it'll work. So can you guys see this? So you remember what strong Cauchy says? You have an absolutely convergent sequence and a positive number. I want you to give me a number n, so that for any finite set that doesn't contain any elements from 1 through n, or n minus, I guess, yeah, 1 through n, doesn't matter. The sum of the absolute value in that set is at most epsilon. Okay, where are we going to get the capital N? From the fact that it's Cauchy. So you take the fact that it's Cauchy, you stick in the fact that it's the absolute value is a convergent sequence. That gives us the Cauchyness. You feed in that epsilon and h epsilon. That gets us a capital M. I don't know why I called it M. Oh, because it's not the capital M. So it gives us a capital M, so that as long as you're past that capital M in both M and N, the absolute value of the series of absolute values summed up to M minus that summed up to N is at most epsilon. And then all we have to do, okay, so use that M for your capital N. Now give me the set, and then take the largest value in that set, which means add them up and add 1. Okay, and then just record what it is. Here's a fact. For all k in the set, k is at most the maximum. Of course, that's the whole point of the maximum. All right, how do you prove that? So give me the k, give me that it's in the set, apply these, sum mem, and then linearith, and hopefully you're happy with that. Now, maybe now that I think about it, there's probably is a way to do this without, if the sequence isn't non-empty. No, there's something I wanted to use about the value of this maximum being large, but whatever. So let's assume that the set is not empty. The set that you gave me to sum over has a value. What that means, the fact that it's not empty means there exists some value that's in it. So choose k0 and hk0. So k0 is some natural number, hk0 is in it. That hk0 is at least m because it's in the set, and every element in the set is at least m. That hk0 is at most the maximum. That's because every element is at most the maximum. And by the way, m is also at most the maximum. Okay, now we're going to take this hm. hm is the Cauchy property. We're going to stick in capital M for little n and the maximum of s for little m. Okay, so that's m and s max. Okay, I want to change the fact that it says series. So this difference of series is just an ICO. ICO from m up to m max. So far, so good? Did I lose anybody? No? Okay, great. So we know that this sum is at most epsilon. The elements in AK are non-negative. Therefore, we can remove the absolute values. Yeah, here. Here, I'm just removing the absolute values. So now, before this rewrite, I knew that I don't know why it's doing something funny. Before the rewrite, I knew that the absolute value of the sum of the absolute values is at most epsilon, but that absolute value is not necessary because it's positive. So that's what this rewrite does. Okay, and then S is inside ICO. S is a subset of that. Why? Because it's obvious. And then the sum over S is at most the sum over the entire interval. That's because one is contained inside the other. That's this sum LE sum of non-neg. And then we know that we want to show that the sum over S in absolute value is at most epsilon. We know that the sum over S is at most the sum over the entire interval. The sum over the entire interval is at most epsilon because of Cauchy. Linearith on those, you have to do a little bit of norm numbing. Linearith on those and you're done. Okay, so now it's the case that S is empty. And then if S is empty, then S is the empty set. And if S is the empty set, then you're summing over the empty set. And norm num seems to do well with summing over empty sets, but bound doesn't. And we get that that's 0. And why is 0 at most epsilon? Because of H epsilon. Okay, that was a blazing fast crash through that, but hopefully it makes sense to you. Any questions, Akil? Yeah.
How do you get the infinity?
How do you get the?
To the infinity, you alternate up and down and
You mean for the proof of? How do you do it for the infinity set? Yeah, you go up to L, and then come down to L over 2, and then go up to 2L, and then come down to L, and then go up to 4L, and come down to. So you have to add in the negative values. That's a great question. I should have said. How do you get to? Where is this? For L equals infinity, do this. So you can get up to L, you can get up to 1, and then come back down to a half. And then you go up to 2, and then come down to 1. And then go up to 4, and then come down to 2. And go up to 8, and come down to 4. So you'll eventually never go back down below 4. And so on.
Why
Sean?
can't you just use like the positive term since you know that they never?
Excellent question. Why can't I just use the positive terms?
Like, what if you just,
It has to be a bijection. I have to use the negative terms. I have to use all the negative terms. If I don't use the negative terms, then it's like our matrix, where I'm only summing, and I say, after you've summed all the positive terms, then go ahead and add the negative terms. No. We got to use them all. So that's why we have to go back down. The question is, how far back down? Whatever, L over 2. I have to use the negative terms for it to be a rearrangement. Excellent. Excellent question. Excellent question. Yeah.
Or like 1 pointer.
As long as the amount by which I go down eventually adds up to infinitely large negative. I can't say go down by a half here and go down by a quarter there and go down by an 8 here. That wouldn't work because I wouldn't be able to use up all the negatives. The negatives are going to add up to whatever. Actually, as long as you, here's something you could do. Okay, you don't have to even do this. You could go up to 1, go positives till 1, and then give me 1 negative. Go positives to 2, give me the next negative. Go positives to 4 and 3, whatever, give me the next negative. Okay, that's another way that you will exhaust all the negatives. It doesn't matter that you go down by, so I said before it's wrong. But as long as you interweave the negatives in such a way that every negative is eventually somewhere. You can't say go wait until infinity and then give you the negative values. So you have to interweave the negative values. Something.
The key idea is like, I guess are we still gonna use like Cauchy, like if you want to, because like the thing I'm concerned about is like how do you, like the magnitudes are like, might not like be so nice when you just kind of like go down.
Oh, you just go it down until you go over 1. That's all you care. If you're talking about the divergent or the convergent.
Well, I guess either case, because like if it was a subsequence, that would be something, right? Like you
Yeah.
can just pick the exact terms you need.
Yeah.
But if it was a
You have to hit
everything, like I'm imagining like you have like your third term is like incredibly large.
Yep.
You can like never use it, but you just
No, you always use the positives and negatives in the order that they arrive. So if your third term is really, really large, if this third term is way up here, you still use it. You still use it in this order. This is called the greedy. I mean, there's all kinds of other rearrangements you could imagine. This is the greedy rearrangement. Add positive terms in the order that you saw them until you get above L. Then add negative terms in the order that you saw them. And the point is, because the terms themselves go to 0, the amount by which you overshoot and undershoot shrinks.
you don't have to stop at one. You just need to get past.
Just get past. Yeah, just get past. Exactly. All right. Gosh, we're completely out of time. This is what always happens, but at least, okay, let me at least show you what happened. Let me at least show you that these things can all be proved. So here's the one about, did you hear the one about the rearrangement? Here's the rearrangement. You use the surjectivity. I'm just writing out what the surjectivity means. And here's the inverse function tau. And then, do some operations there. And then let's just do the last one. Because as I told you, I didn't finish the other one myself. And I want to move on because we have to hit other topics. But the first idea is give me the limit. So now we're on the Cauchy. The absolute convergence means that you can reorder anything. So given that it's absolutely convergent, it's convergent. Given that it's convergent, it converges to something. So then we're done. Give me that epsilon. We're going to use the Cauchiness with epsilon over 2 and the fact that the sequence itself converges with an epsilon over 2. And then the fact that you can eventually cover gives you an N3 and go beyond N1 and N2 and N3, where N3 depends on N1 and N2. This is the subtle stuff that you only get to when you're really formalizing it. So please go through this proof that you'll see in GitHub, put it in line by line into the game and see what happens. Then you give me the L, you do a little bit of analysis, and you get the theorem. So let me just show you what the last step of the theorem looks like. We're still trying to prove that the series for reordered up to n differs from the series of A reordered up to n1 plus n2. I added and subtracted that, so minus L is that less than epsilon. And F1 says break that up by the triangle inequality. Why are these two things small? Because they differ by the sum over the difference in the image between the image and the range. The image and the range is contained in some even smaller set, and that's less than epsilon over 2 because of Cauchy. And the other thing is less than epsilon over 2 because it converges, and you put the 2 epsilon over 2's together and you get it. All right, that's it for series. On to functions.